In this video, I'm going to go through the Bell's inequality and the Bell's theorem in general. So the goal of this video is to derive the famous Bell inequality and understand its implication. So if you watch my previous video on the EPR paradox, you'll know that Einstein, Podolsky, Rosen, they did not doubt that quantum mechanics is correct. As far as it goes, they just claim that it's incomplete because their position is that they think that there is some hidden variable that quantum mechanics is not accounting. So instead of believing that quantum mechanics fundamentally is probabilistic, they believe that there is some hidden variable that already determine the particle's spin, position, whatever value you're trying to measure, and that this hidden variable is not part of quantum mechanics yet, and they are trying to find this hidden variable. So physicists has been working on that ever since, until 1964. A famous physicist named John Stuart Bell proved that any local hidden variable theory is incompatible with quantum mechanics. And I'm going to just explain what that means. So, if you remember, in my previous video, I talked about how when you have a pi meson, and then it can be then one electron, it can decay into one electron and one positron, and the angular momentum must be conserved, meaning that their net spin must be zero. So one must be spin up, the other one must be spin down. So remember from my previous video, that was the simplified version of the EPRB experiment or EPR paradox. But in this case, John proposed a different way. So instead of he proposed that we have the detector oriented in this way. I'm just going to draw and explain. So the way John did it was that instead of just considering that the particles go opposite direction or they're aligned, he also considered cases where he can orientate these detectors in a certain way. So instead of orienting the electron and the positron detector along the same direction, he proposed that we are able to rotate these detector plates, which I'm drawing here. These are detector plates independently. So these are able to rotate. And I have two arrows here. The first arrow here is A, second arrow here is B. So these are unit vectors. It basically gives the direction in which we're measuring the spin. And that really matters because back in chapter 4.4, when you consider that for a system of identical 1/2 spin particles, the direction at which you measure the spin does matter. Like if this is spin up and you measure orthogonally, right? Like this is spin up, you measure orthogonally to it, then the probability of obtaining spin up and spin down becomes 50-50. Or if you measure at, let's say, this is 60 degree, then the spin up chance becomes 3/4 and the spin down chance becomes 1/4. So what that means is that the implication of that is that the angle at which you measure the spin influences the probability of measuring the particle and the particle being in spin up or spin down. So the angle does matter. So that's what he introduced in this case. But in this case, obviously you can still return to what we were working before by simply aligning A and B. Because if they're aligned, then it is the exact same experiment as the one I proposed in my previous video, where one is +1 and the other one is -1. That's the result of the spin. So he wanted to look at the product of the spins. So for example, you have a table where it's electrons and positrons and product, right? So in this case, let's say you measure electron to be spin up, so you have +1, positron to be spin down, so -1, then the product will be -1, right? Or another case of scenario where they both measure +1 and the product becomes +1, or -1 plus 1 -1. So the list continues and goes like this. So a table of many results for many of these decays might look like what I've drawn here. So Bell proposed to calculate the average value of the product of the spin for a given detector. And we call this average value PAB, where A is the unit vector of the detector for electron, and B is the unit vector for detector for the positron. So this PAB means the average value of the product of the spins, because you're taking multiple trials, right? And then you can conclude the average value of all of these trials that you have obtained, right? Because you have, let's say you design an experiment where you do this sort of decay multiple times and you record them down to a table. So the average value of the product of all of your recorded result is going to be this PAB, which is the average value of the product of the spin. So the average value part is important. So when the detectors are parallel, in other words, if A is equal to B, if A is equal to B, so this means that they point in the same direction. So A is equal to B. We recover the original configuration, which is one is spin up, the other one is spin down. So the product is always -1. So PAB. So if B is equal to A, right, then this is just become PAA, which is equal to -1. This is because when the detectors are parallel, you get the case in which we're discussing before, where one is always spin up, the other one is always spin down. So the product of a spin up +1 and a spin down -1. So +1 times -1 is always -1, right? So that's why the average value of the product of the spin here is -1, because no matter whether electron to be spin up, positron to be spin down, or the vice versa, the product of them will always be -1. If the case is one is spin up, the other one is spin down. So by the same token, if they're anti-parallel, which is the case if B is equal to -A, then the product is +1. Then the product is +1. When I say B is equal to -A, I mean it forms like, let's say this is B and this is A, right? So you can see that there's a 180 degrees between them. So that's what I mean by when I say B is equal to -A, because -A would just look like this, right? And is equal to B, in this case, which I have drawn. So for any arbitrary orientation, quantum mechanics predicts, so this is very important. So quantum mechanics predicts the following formula, which is PAB is equal to -A times B. So what this means is that, well, first of all, the PAB, as I have said multiple times, is the average value of the product of the spin, is the negative of A times B, where A is the orientation, A and B are the orientation of detector A and detector B. So what Bell had discovered is that this result right here is always incompatible with any local hidden variable theory, which is what we're trying to say here. So the argument is very simple, which I'm gonna show the math just right now. So we want to introduce this hidden variable, which we call lambda. Let's go to the next page. So we introduce this hidden variable lambda. Because that's what the hidden variable theory is about, right? There is some sort of hidden variable within the equation that we do not know yet. In this case, we're going to denote it as lambda. And this lambda already encodes or already has the information whether the electron or the positron is going to be spin up or spin down, right? That's what the realists believe, is that this hidden variable contains information that is already predetermined, and there is no probabilistic at the very fundamental. So suppose we introduce this hidden variable lambda, and then we suppose further that the outcome of the electron measurement is independent of the orientation of the positron detector. What that means is that if you scroll back into our example, it means the measurement we make on this electron to determine if it's spin up or spin down is independent of the orientation we have on the positron, so on the orientation which is B in this case, right? So that's what it tells us. The outcome of our measurement on electron is independent of the orientation of the positron detector. The reason why is because this is the locality assumption. Remember, the locality assumption means that no influence can travel faster than the speed of light. In this case, if you follow that assumption, it means that no matter how far away your electron or positron is, the measurement that you make on the electron has no influences, or has nothing to do with the orientation you have on the positron, because you're assuming locality here. You're assuming that. So imagine you have this Mason decay, and they're positioned 10 light years away apart from each other, and then the locality assumption would assume that each electron and positron already carry their own hidden variable, so that when you make the measurement of the electron or the positron, the result is already predetermined. So that is the locality assumption, which is that the outcome of the electron measurement is independent of the orientation of the positron detector. So like I said, there exists a function A, which has a variable A and lambda, which determines the electron, the result of the electron measurement. And there is some other function B, which has variable B and lambda for the positron measurement. And you can see the electron, the outcome of the electron relies on the direction you measure it at, right? Which is what A is resembling, and also this hidden variable also influences that. So what this says is that these two basically, A here would just represent the result of the electron measurement, and B here would result in the positron measurement. And we know that for both, they're going to be equal to plus minus 1. So A lambda is equal to plus minus 1, B lambda is equal to plus minus 1, right? Because we have plus 1 it resembles spin up, negative 1 resembles spin down, and the electron can either be spin up or spin down, and there's no limitation on them. So therefore it's going to be a plus minus 1 and it just intuitively makes sense, because there is no restriction whatsoever on electron or positron, or whether one can be spin up, the other one can be spin down, right? They can both be spin up or spin down. There's no restriction on that. So let's further expand this. So remember, when the case when A is equal to B, like I mentioned above, what happens when A equals to B is that they equal to the negative of each other. So what that means is that if I have A lambda, this is going to be equal to negative B lambda. And since A is equal to B, A lambda is just going to be equal to negative B A lambda. So what does this imply? This implies that whenever A is equal to B, or that they're parallel, they're anti-parallel to each other. So if you find A to be spin up B will always be spin down, and vice versa. So when A and B are parallel to each other, we know that the result of the measurement will just always be the opposite of each other. Like if you measure the electron to be +1, then the positron will be -1, and vice versa. So that's what's going on here, is the result that we have here. It says that. So the results are perfectly anti-correlated. So now we're going to define something called the average or the excitation of the product of the two measurement outcomes. So you should have known from previous quantum mechanics that you've learned that, well, since in this case, what are we going to have in our PAB? Well, it's going to be influenced by the hidden variable and A lambda, B lambda, right? And D lambda. And this P lambda here represents probability density of lambda. Because lambda lambda has to have a probability density because we're making multiple measurements, right? And we do not exactly know how the hidden variable affects the result, but we know that when taken at a large number, it has sort of a probability density. And just like any probability density, when you integrate P lambda D lambda, it's going to be equal to 1. This is the normalization that's ensured. So this, what we have here, is the excitation of the product of two measurable outcome. So let's dive deeper into it. Well, if we go back a little bit from this formula, if we follow the same logic, how we got this formula right here, then we can say the same about B. So B lambda is going to equal to -A B lambda. So this is what we're gonna have here, and this is the exact same thing as the formula we have here, but the signs are flipped, and they resemble the same thing, and you obtain the same result following the same logic, because when B is equal to A, then B is equal to B. No, if A is equal to B, then B is equal to B, right? It's equal to itself. So if they're parallel to each other, then whatever outcome you obtain from the positron is the outcome for will always be the negative of the outcome from the electron, because it's either +1 or -1. So we can use the same logic to obtain this equation. Hence, we can replace our PAB. So our PAB now is going to become integral P lambda, so probability density function, A lambda times B lambda, D lambda is going to equal to integral P lambda A lambda. So this does not change, but our B lambda can turn into a negative A B lambda. So negative A B lambda D lambda. And if we just take the negative sign now, it just implies our PAB is going to be a negative integral P lambda A lambda A B lambda. I'm sort of following I'm sort of deriving and following the same step as the textbook, and as I put in my description, the textbook I'm using is Griffiths Quantum Mechanics, and this is chapter 12.12. But this textbook do skip a lot of steps, which is what I'm going to cover here, so I hope you guys follow. So we obtained this, which on the textbook is 12.8, the formula 12.8, and now, just like how we propose A and B to be a unit vector, now we can look at something called C. So C is another unit vector. So unit vector C. For unit vector C, well, if we know PAB is equal to negative P lambda A lambda A B lambda D lambda, then our PAC is going to be negative P lambda A lambda A and then C lambda D lambda, right? We're just replacing our B here with the C. So how we came up with this follow the exact logic of how we came up with this, but we're just swapping the B with the C, because the only thing that changes is that we have another unit vector which we define as C. So now we have defined PAB and PAC. Now we're gonna minus them. So PAB minus PAC. So what is this gonna equal to? This is gonna equal to negative P lambda A lambda A B lambda D lambda minus, and then another minus sign inside, right? From this minus lambda D lambda, and then close the bracket up, I think, yeah. And since we have two negative here, that makes it positive, so this is going to be I probably should be skipping these steps, because I'm still going to write it down and you guys can follow, but these are not very complicated mathematics here, and it is in fact very simple, which is why this result is so stunning. It's because how the implication that it has and how simple the math be. So right now this then becomes negative integral. So we want to group up the like terms. I'm just doing algebra here, and you guys should be familiar with it, right? I simply just group the terms here. So I made the two individual integral into one, and this is going to be equal to negative P lambda A lambda, right? You just take the A lambda out again from this equation, then you have A B lambda minus A C lambda D lambda. So this is what we have for PAB minus PAC, where C is another unit vector, just like B and A. Well, since we know that A B lambda and A C lambda is gonna be are both plus minus 1, right? We know this because for whatever detector you put down, the measurement is always going to be a spin up or a spin down. So it's always going to be a plus minus 1, regardless of what detector orientation you're going to look at, right? So therefore, if we know the result is always going to be plus minus 1, then let me ask you, if you square this, what do you get? What do you get? Oh, you get 1, right? Because if it's plus minus 1, when it's 1, you square it, you get 1. When it's negative 1, you square it, you get 1. So the square of AB lambda is just going to be 1. And this is pretty big and important, because if you look at the integrand, so if you look at what we have inside the integral, let's move it down. So AB lambda minus AC lambda, right? If we know that AB lambda squared is equal to 1, we can make this becomes AB lambda times 1 minus AB lambda AC lambda. Because if you multiply this, you get the same thing as this, right? This goes to here, multiply by 1, you get it here, and then this multiplied by AB lambda, you just get 1. So it just becomes AB lambda and AC lambda. So that's what I'm doing here. So once we have this, what we can what we could do is that, well, this is only this part of the equation, right? And there's also a lambda in front of it. So now our total, then this whole expression becomes a negative integral p lambda times a lambda. So this is from here, and this inside becomes this thing right here. So times a b lambda 1 minus a b lambda a c lambda. This is what we have here. And this is the 12.10 on the textbook. And now we can take a look at the absolute value. So before we take a look at the absolute value, we want to look at the absolute value of a lambda times a b lambda. This is gonna be equal to 1, right? Because no matter what a and b is, the possible combination are what? The possible combination is 1, 1. So absolute value of 1 times 1 is 1. Another possible combination is negative 1 and 1. So negative 1 times 1 is negative 1. The absolute value of negative 1 is 1. And the last possible combination is negative 1 and negative 1. And negative 1 times negative 1 just be 1. The absolute value of 1. So in any case, we have a lambda and a b lambda, you always get 1. So this is one of the results. So let's take absolute value of our PAB minus our PAC, which is equal to the absolute value of this whole thing we have here. So negative P lambda times A lambda, A B lambda, 1 minus A B lambda, A C lambda is what we have here. And since we have, let's say, negative x inside an absolute value, this is just going to be x, right? This expression is true, so now this expression just becomes, so PA minus AB minus PAC is just going to be, so we're just removing the negative sign here. One minus A B lambda A C lambda, and then D lambda. And from from the mathematical property, which is called the triangular inequality, you might have learned since that when you have the absolute value of a whole integral, so let's say f of t dt, this is always going to be smaller or equal to if you shift the absolute value symbol inside. So this inequality is a result from math. I'm not going to prove it here, but if you want to know this inequality, you can just Google triangular inequality and integral, and this will just pop up on the feed. So from this result, we're going to get PAB minus PAC is going to be smaller than equal to, well, since this, our absolute value of PAB minus PAC is already equal to this, this is going to be equal to just integral, but the inside is, this is going to be, take the probability density function out, absolute value of 1 minus A B lambda A C lambda times A lambda A B lambda, and absolute value D lambda is what we're going to have here. And this is the equation 12.11 on the textbooks. And what we're going to have here is that, as I already discussed, the absolute value of AA lambda times AB lambda is just going to be 1. I already discussed it, the reason why here. So this can further be simplified into this. Smaller than or equal to lambda px, lambda p lambda 1 minus a b lambda a c lambda d lambda. So this is what we have so far. And the reason why we are able to remove the absolute value sign is because what we have inside for this expression, 1 minus a b lambda times a c lambda is always bigger than or equal to 0. So it's never negative whenever each a, or negative 1, whenever each a is plus or minus 1, right? Because for this, you can get a result of 1, right? They can both be 1 or negative 1, so in that case, the product is going to be 1. So 1 minus 1 is bigger than or equal to 0. Or in the case where you get negative 1, like 1 is spin up, the other one is spin down, so you get negative 1 times 1, which is negative 1, so 1 minus negative 1 is going to be 2. So in all scenario, here we have it bigger than 0, so therefore we're able to remove the absolute value sign we have here. So now we can move on to the next part, which is the final part, which is the important part that we get our inequality from. So let's further examine this integral. Write it down again. Oh, what happened to? Okay. So let's further examine this integral. P lambda 1 minus a b lambda, and we have to simplify this more. Well, the first step we can simplify is that you can multiply p lambda into the equation. So what you get now is 2 integral d lambda minus, remember we're just doing some basic calculus here. There's nothing hard about any of this, right? We just move the p lambda into it. That's what we're doing. Now we split it. Just like how we combined them into 1 before, now we're splitting it apart into 2. And remember, due to the normalization property of the probability density function, this is just going to be equal to 1. So the important thing to look at is going to be this. So we know that we know that PBC is going to be negative integral lambda a b lambda a c lambda d lambda, right? Where do I get this? If you go all the way back up, yeah, similar logic as this, but you have to replace it with b and c. Same logic. So let's continue. So this is negative, right? So negative PBC is equal to positive. The same thing. And this is what we want to replace the expression we have here. So now you have this is equal to 1 minus P AB equal to 1 plus P A B. So you have the final inequality, which is the Bell's inequality, the famously known Bell's inequality, which is the following: PAB minus PAC smaller than or equal to 1 plus PBC. And we finish our derivation at this point. So this is 12.12 on the textbook, which is the famously known as Bell inequality. And this holds for any local hidden variable theory. So this inequality holds for any hidden variable theory. So any local hidden variable theory you have must match this inequality. And we can look at a simple case to show that why this is not compatible with quantum mechanics. So suppose we have three vectors that lies in a plane. So we have vector B, vector A, and then at a 45 degrees we have vector C. So just 45 degrees to both sides. And according to quantum mechanics, PAB is equal to 0, right? Because when they're orthogonal, the average value obtained is going to be 0. So back in chapter 4, we also learned the formula for PAB is equal to negative cos theta, where theta is the angle between A and B, right? Well, for this case, you can clearly see that PAB is equal to 0. That's 1. So what about PAC and PBC? What about the relation between B and C and A and C? So what happens here? Well, PAC is what? PAC or PBC, they're the same thing because they're forming the same angle, is equal to negative cos 45 degrees, which is equal to negative square root of 2 over 2, which is approximately negative 0.7007. So what I have calculated so far for here is a result from the quantum mechanics, and let's see if it satisfies our Bell's inequality. So for our Bell inequality, we have PAB. So let's copy it down here. So for our Bell inequality, which has to apply to all local hidden variable theory, for our PAB, this is going to be 0. And for our AC, I read like an L, which is kind of bad writing by me, but our PAC is going to be negative 0.707, and since we have the absolute value, this whole left term is just going to be 0.07 is bigger than or equal to, well, 1. PBC is negative 707, so minus 0.707, so that's like 0.293. So clearly this inequality does not work because 0.293 is not bigger than 0.707. And that is pretty profound, because what this example has shown is that the local hidden variable theory is not compatible with quantum mechanics, because this result here is what we attain from quantum mechanics, and this inequality is for the hidden variable theory to satisfy, and it does not satisfy in this case. Therefore, the local hidden variable theory is not compatible with quantum mechanics. So I'm now going to start talking about the implication of this. So there's going to be less math and more talking. So the EPR paradox. So this whole thing of what we're trying to do here is this debate between the realist position and the orthodox position, right? The realists believe that there is this hidden variable that already predetermined the particle's position and momentum in these, or spin in cases like that. They believe that there is already a variable determined, just like classical mechanics. It's already determined. It's just that quantum mechanics does not include that variable. So therefore, so it's not entirely correct to say that realists think quantum mechanics is wrong. It's rather that they think it's incomplete, it's missing a hidden variable. That's what they think. And what John has proved here is that it's like this all-out battle between quantum mechanics or between the orthodox view and the realist view, where only one can survive. In this case, through multiple experimentation, it shows that the quantum mechanics or the orthodox view survive, and that is the nature or the fundamental of our world. So if the realists were to be correct, then not only is quantum mechanics incomplete, it is just downright wrong. So you cannot have both at the same time. So if the local hidden variable theory, more accurately, is correct, then quantum mechanics is entirely wrong. On the other hand, if quantum mechanics is right, then no hidden variable theory is going to be right. Like they cannot both be right at the same time. This is what this Bell inequality shows. That's the summarization. And many experiments has been done to test this Bell's inequality, and they were performed in the 1960s and the 1970s. In fact, I think the Reason Nobel Prize during 2020, or was it 2022, that was it was given to these scientists that contributed to experimenting with Bell's inequality. So the detail do not concern us here, but the experimental confirmation of quantum mechanics came as something of shock to the scientific community. So Bell inequality multiple experiments were done, and they're in excellent agreement with the prediction of quantum mechanics, and they're inconsistent with Bell inequality by a wide margin, which the hidden variable theory represents. So basically, from our experimentation results, we're almost certain to believe that quantum mechanics is the correct theory here. So ironically, the scientific community is shocked at that because it spelled the demise of realism, as the textbook described. Like a lot of physicists have already adapted to this. Like I actually recently saw a video of Feynman, where audience of Feynman asked him, okay, what does Feynman think about the Bell's inequality? And he says it's no big deal because the physicists like his levels already, like when they work on their electrodynamics or higher level of quantum mechanics, they already established all their theory on an axiom of orthodox view. So it came to no surprise that a realist interpretation would eventually fail somewhere. So that's why he said it was no big deal, but I think it's actually pretty big deal. But he's got a point, because there weren't a lot of physicists working on the hidden variable theory. It's not like everybody was working on it and then John disproved it and everybody's just shocked and then disproved. It's more like the majority of the physicists has already adapted to the orthodox view of the quantum mechanics, and very few were working on the hidden variable theory. And what John did was simply deny those people to mathematically prove that quantum mechanics, or the orthodox view, cannot coexist with the hidden variable theory. But there is hope for them, because one of our initial assumption for Bell's inequality, we talk about locality, which is in this case of the Bell inequality, we assume that light speed is constant. Where another hope for them would be a possibility of non-local hidden variable theory, which Bell's theorem do not apply to. So I'm not sure if that has any real result out right now, and I'm not familiar with it, but if you really want to know, you should do some research. But the real shock was the demonstration that nature itself is fundamentally non-local. So non-locality in the form of the instantaneous collapse of the wave function. So that is true. So that has been proven to be true. Like when Einstein proposed such a paradox, they felt it was absurd to believe that a wave function could instantly collapse at such large distance. But that is actually what we observe in real life. So that is the true answer. And Einstein was indeed proved wrong for his deterministic view, as we know so far. Maybe one day Einstein will be correct again, because he's just a smart dude. But for now, as we understand it, the nature itself is fundamentally non-local, which is something like so non-locality in the form of the instantaneous collapse of the wave function has always been a feature of the orthodox interpretation. Before the experiments in these inequalities, there was certain hope that quantum non-locality is somehow like a non-physical artifact of formalism. So there was hope before these experiments and these inequalities that maybe it's just our human understanding or from formalism in our mathematics that we somehow haven't figured out the hidden variable part yet. But after these experiments and these inequality, wow, the universe is really non-local, or in the case of a wave function, it doesn't have to be local, and that whole can no longer be sustained, and we're obligated to re-examine our objection to instantaneous action at a distance. So why is, if such spooky action really does happen in reality, then why our physicists seems to not be so concerned about it? Because at face value, it seems that this spontaneous reaction over a very long distance seems to violate special relativity. However, it is not catastrophic for the following reason. First of all, you want to understand something, that there is actually no faster than light communication here. Right? Although the wave function itself is instantaneous, it does not allow any observer to understand useful information faster than the speed of light. So let me explain this. So in the case of this pi mason, where it sends an electron and a positron, right? And let's say they're like 100 light years away. So there's 50 light year here, 50 light year here. So if you measure the electron's information, so if you measure it to be spin up, right, for you to send that information back to the observer, that speed is still finite, right? So although you have measured your electron to be spin up, and somehow instantaneously the positron knows it to be spin down, but that's a very, very wrong way to describe it, because when I say the positron knows that it's going to be spin down, we assume as if it has some sort of consciousness, which it does not, right? For an observer at the positron ends, when I look at the positron, it's still a 50-50% for him. So when two electrons, in this case, when the electron and positron becomes entangled and they separate over such a large distance, no real information can be encoded so that during this process, the information can travel faster than the speed of light. So there is no control over which outcome the first observer sees. It's a random result. And there is no way to influence what outcome appears at a distant location. So from my point of view, the electron measurement is going to be random, and from the positron guy's point of view, it's going to be random as well. There is no information, and whether the positron or electron is going to be spin up or spin down, only the particle knows. Again, that's the wrong way to say it, but you kind of sort of have to get the idea. Although even though the other particle state is instantly determined in the quantum sense, but there is no outcome. There's no control over which outcome the first observer see, which is my position at the electron, and there's no way for me to influence what outcome appears at the positron location, which is the distance guy at the positron measuring it. So therefore, there is no possibility for me to decode any message until classical information is also exchanged. So in that sense, let's say after I measure, I send a signal, and it travels 100 light years to reach that guy. Now that is a classical information sense. Now he knows, right? But by the time he knows, 100 years already passed. So that does not violate the speed of light or special relativity in any sense. So that is the reason why the so-called spooky action at a distance, the instantaneous collapse of the wave function is not as catastrophic as it seems. So as you can see at the end of the textbook, it talks about two types of influences: the causal variety, which produce actual changes in some property, in some physical property of the receiver, detectable by measurements on that subsystem alone, and an ephemeral kind, which do not transmit energy or information, and for which only evident is a correlation in the data taken on the two separate subsystems, a correlation which by its nature cannot be detected by examining either this law, and the wave function is clearly the latter part, right? Although it is indeed instantaneous reaction at a very large distance. In fact, there is no distance limit, but there is no way for you to encode any information into it because the information is only known after you measure on one side, right? It's in the superposition of both sides. So therefore, there is no way for you to encode information into it, and therefore no way for information to reach the other side in a classical sense. So therefore, the so-called no information can travel faster than the speed of light is indeed not violated in this case. So rather than sort of not sure if you guys seen the clickbaits on YouTube, a lot of people, a lot of these articles sometimes I read, it's like they describe this as such a catastrophic event of like flipping the entire physics world over, but once you really sit down and examine what is going on, then you realize it's in the quantum sense, it's in the classical sense, nothing has been violated, in the sense that no information, still information travels fastest at the speed of light, and no limit has been broken. So it's not really as catastrophic as it seems. But another problem I want to point out is the so-called collapse of the wave function. So this is at the end of the chapter of the textbooks, and you realize that only in this chapter the author briefly touches on the idea of collapse, because it's not as well defined as if you're interested in this idea, you can go watch Sir Roger Penrose, which is a famous physicist, and his view on this collapse of the wave function, which is that the Schrödinger's equation, this whole quantum mechanics, really does not describe what happens when we say the wave function collapse. Like that is not part of the quantum mechanics, which is, and there are many interpretations to what happens after the collapse, right? There is the interesting many world interpretation, which is that each time you observe, or each time the wave function collapse, it splits into two universes. You know, if the electrons in the superposition of position 1 and 2, and when you make the measurement determined it to be position 1, there's actually another multiverse with determined value of the particle at position 2. So there are many interpretations to the so-called collapse of the wave function, but still not yet to this day, 2025. I don't think we can still very confidently explain what really goes on when we or this nature of the so-called collapse of the wave function matter is something that our human struggles with right now, our physics world struggle with. And if you haven't made it this far, congratulations, because most people probably stop before 5 minutes. But if you really made it this far, I hope you learned something. If you have any questions, feel free to ask me down in the comment section. And thank you guys for listening. I'll see you guys next time.